What we are going to do today is talk a lot about design theory. And exactly as what you were doing for the exercise, one of the first things you end up doing is you're defining your functional dependencies. And at the end of class last Monday, we talked about what a functional dependency is. Basically, it's a very simple definition of X implies Y. Meaning that if you have two tuples where the left-hand side has the same values, the right-hand side should also have the same values. And we use this example to kind of get warmed up, right? It basically tells you what things are related. So we said that, for example, for a given music group, the genre is about the music group. So music group implies the genre. Or if you look at the definition, if you find two tuples with the same music group, they have to have the same genre, right? Music group implies genre. But, for example, the baked joint has to do with a music group and an artist. So, given the same music group and artist, you have to have the same date joint. If you had two tuples with the same music group and the artist, they should have the same date joint. And we talked about, for example, date of birth, which we don't have here. Date of birth has to do with the artist only. So if you have two tuples with the same artist name, you have to have the same date of birth, right? So this is the basic idea of a functional dependency. So one way to look at that is to look at a relation like this one, which basically is, you kind of can tell that all of these attributes don't belong in the same relation, right? But the point is that it's not clear how you find the right combination, because if you separated them first, there's no way to put them together, because as you will see, what we are going to look at is how to separate it. So there's a design methodology that starts with almost all your attributes and then finds a way to divide them into relations. That's what we call normalization. And they call this the universal relation, which we know is not necessarily what I want to store, but this is a good way to think about what things belong in a single relation and which things don't. So I threw in all attributes I can think of in here, but remember, these attributes will take simple values, right? So for an episode ID, you're going to have a value 1. So you're not going to have 1, 2, and 3. So basically, I tried to throw in some rules. I hope the rules make some sense. And then we tried to write functional dependencies that are valid for these. So let's try to write some that make sense. And let's try to find kind of a crucial one. So for example, if I have show ID alone, what is implied by show ID? All right? But the TV network is not implied because sometimes the TV network changes, right? The same show moves from, Fox to Netflix, for example. So, okay, is anything else implied by show ID? Show ID? Oh, show ended. That is correct. Okay. What is the next thing I should think about? How about show ID together with TV network? Is it the TV network that decides, or is it the season? Right? We are going to talk about this in a second. So let's say show ID and season number implies TV network. Anything else? How about show ID and TV network? Do they apply the season? No, because you may have multiple seasons, right? Okay, so how about the episodes? How do I find the episode episode date aired. That should be fixed for. Remember TV. So okay, so now you will learn to kind of look back, right? TV network actually is implied by show ID and season number, right? So go back in time. Show ID, season number, and episode number, right? So given those three things, because episodes are 1, 2, and 3, not 1, 1, not 1, 1, 1, 2, 1, 3. So show ID. This example is based on my extensive use of IMDb. Season number and episode number. Given these three, I can find things like episode date aired, and episode summary. All right. And the episode cast actor ID, that's fine, right? No, that would mean that there is a single episode, there's a single cast person, right? That would not work. All right. What's next? So how about actor name and actor URL? So how about this? Something like this. You have an actor ID unique to each actor. Given the actor ID, you can find their name and URL. I don't know if URL is unique. If URL is unique, I can write the same thing for URL, right? Given the URL, I find the name and the ID. I do not know if the URL is unique because I don't say anything. Say it again. But is it unique? Like, can two actors have the same URL? I don't know. All right, so I haven't said it. Let's not make an assumption. In real life, most likely. Okay. All right. So what happens to character names? Character names are not unique, right? But I can tell that given a episode actor ID for a specific episode, there is a unique order, right? So I can say something like show ID I regret the length of these names, implies episode cast order. Okay. But it does not imply the character because even in a single episode, that actor may play multiple characters. In fact, nothing applies character name, which is kind of interesting. It will leave you unsettled, but I'm going to leave it like that, and we will see what happens with that. Nothing really implies the character name. And this is one of my better examples. Any questions so far? Yes. So if that is true, we're going to put it in, then we will see what to do with that, right? So let's say that it is in fact true that actor URL also implies actor ID and actor name, right? There's nothing wrong with that. You can have multiple such things. We will see what that means. Okay? Questions?
Yeah. So, basically, the rule is a subset. So, for example, show ID season number, you have PD numbers, but you also have show name. So, do we list that?
So the show name implies what?
Show name.
So one of the things we will see right now, okay, so shortly after this, is some things are necessary and some things are not, right? But when you're first designing, you can list everything that makes sense to you, but then we will see the rules for simplifying them, okay? So the show name does not imply show ID.
No, I'm saying show ID and season number will also get you show name and show.
That is correct. That was actually a great question last time too, right? So for example, there was a question last time as well, that it is also the case that, let me write this down, show name, show ID. This may not be the exact one you told, but it's an example. Also implies show ended, right? So this is true because if you have the same show ID and show name, you also get whether it's show ended or not. But what we will see is that you do not need this. If you have these, you can derive this one. Okay? So we will learn the rules immediately after this. Okay? All right. So let's write the same thing for the classes. So far, nobody objects, so I'm happy. I was doing office hours yesterday, and we were doing the spring homework for relational algebra. I realized that was a much better homework than the one I gave. I said that 3 years ago, whoever wrote that homework was much smarter than me. But all right, let's do the class. So. Any ideas? Well, let's start with CRN. At least we know something about CRN. What does CRN imply? So does it imply topic code and course code? Yeah, right? Topic code, course code. Does it imply course name? Yes. Section ID, semester, and year. To my knowledge, they do not recycle CRNs. Okay. Does it imply instructor ID? No, because given a single section, you may have multiple instructors. Right. Okay. Instructor ID, however, implies instructor name. So does the CRN imply classroom? Sure. Oh, you mean like if it has a lab in a different location? Yeah, I didn't write that down here though. All right. Does it imply textbook? No, because there could be multiple textbooks. Okay. But the textbook ISBN name and the author. And in fact, topic code and course code implies course name, right? So topic code and course code implies course name. So if you're starting to kind of see the thing, you don't actually need it here because you can get it from this one. Do we have anything else that we can say?
Is that true for the topic classes that have the same course code and topic code and have different course names?
That is true. I like that. So the question was, for topic courses, sometimes it is not the same course name, actually, right? So that is actually true. So we can say that this is actually not necessarily true. Real life is much more complex than what we would like it to be, so we can get rid of that. That is true. No, there's always an objection stuff I haven't thought. Yes? Textbook with multiple authors. Do I say that? That's true. All right. Well, do we agree that the textbook name is unique? All right. That was repudiated. So I will put the course name back here because that is true. Okay. Anything else you can tell me? All right. How about given a CRN and a meeting day, there's a specific meeting time and a classroom. Do you agree? For a specific classroom, right? For a specific class, specific day, there's a time and a All right, so that didn't work either. All right, how about that? How about you have CRN meeting day, meeting time, you have a classroom. Buying this? All right, that's good. All right, finally I can sell this one. CRN meeting days and meeting time. We have a specific classroom. So what did we learn from this exercise? This is not like a straightforward and simple thing, right? It does require thinking, it does require talking to the customer, it does require, it's an iterative process, yes. But the meeting days is not a single value, right? So I'm going to store a tuple for Monday at 6, Monday at 2. So I'm not going to store it as a single string. I'm going to store it because that would not work, right? Because you have to basically store. If you look at SIS, you have this day at this location, this day at that location. Yes. That is true. I don't really know. You probably can store it either way. You can either store it MR or you can just store it M. This will allow both, right? Okay? You're good? So this is the idea that you have a relation and you are trying to understand what are the rules about this relation. And as you get more comfortable, you will actually start to put them in different relations without going through this exercise. But sometimes if you are not sure, this is the exercise to go through to figure out whether they belong in the same relation or not. So the first thing that we would like to do, given these functional dependencies, we can actually find the keys. Okay? The reason that we are defining all of these is to really understand the keys for our relations. And once we understand the key, we are going to basically next talk about whether, given the key, this is a good relation or not. Okay? What do you think about the two relations we just did? Are they good relations? They're awful relations. Okay? But we will see why in a second. Okay. So the whole point of doing functional dependencies is to define keys. So if life was very simple, and you had a relation, let's say, student, ID, name, major, and year. And what I do know is that ID implies name, major, and year. Then I can say that ID is a key because we said that no two tuples should have the same value for ID and key, right? So that's what we basically said for key was attributes that are unique, right? So no two tuples have the same value for attributes in key. Okay. Or you can say the same thing, but express it as differently. So I'm going to say A1, AN is key if A1 through AN implies all attributes in the relation. So let's convince ourselves that these two are actually the same thing. Okay? So if the attribute implies all the other attributes in the relation, you cannot have two different tuples that have the same values for the left-hand side, but different values for the right-hand side, right? So you cannot have two tuples. So this is, for example, you cannot have two tuples with the same ID, but different names, right? This is not allowed because ID implies name. So the only thing that you can have is the same major and the same year, right? So since ID implies name, major, and year, it says that if I'm given the ID, if I have two tuples with the same ID, these are also going to be the same, so it's basically the same tuple. So if this implies everything else, then all the attributes, all the tuples are guaranteed to have a unique value for this one. Okay, so does that make sense? I know that it's kind of, I'm saying the same thing in two totally different ways, right? One says that you cannot have two separate tuples with the different values for the key. The other one says that you cannot have, if you have two tuples with the same values for this side, then for this side, then they have to have the same values, so you're actually looking at the same tuple, so you cannot have two different tuples. Okay? So basically the point of a key is that it's an attribute that implies everything else. Okay? But then the question was asked, okay, if this is true, I can also write other things. I can also say, so let's say that I have ID implies name, major, and year. I can also say ID and name together implies major and year. Okay. So if the top is true, the bottom is also true. Why is that the case? Because if you have two tuples with the same ID, then you are guaranteed to have the same name, major, and year, right? So the first one says that if you have the same ID, so if you have ID1 and ID1, according to the first one, I am guaranteed to have the same values for these. The second rule says, suppose you have two tuples with the same ID and name, like these two. These are guaranteed to be the same, which is the same thing, right? I mean, it's basically, the second one is implied by the first one, yes. Well, just forget it. From now on, it's only my way of relations. This is why I'm going to move away from ID, name, and major to A, B, and C. But yes, I'm not saying this is the best model at all. Dual majors are stored separately. How many of you had a, CAP report that was actually errors? You had errors? Yeah, because it's very difficult to do this stuff. All right. So the point is that given one functional dependency, you can get the others. So because of that, we are going to define some rules and figure out which ones are the good ones, meaning that they are useful piece of information. The others are just extra that you can get. Okay. So from this point on, I'm going to get rid of ID and so on, and I'm going to use A, B, C, D, but they represent real attributes, right? So if you, for example, have A implies B, and B implies C, right? Then I can also say, what else can I say? A implies C, okay? So this is true for not a single attribute, but any sets of attributes. So even if I had, for example, A and B implies C, and C implies D and E, then I can also get A and B implies D and E, right? If you think about why, it's very simple, right? If you have two tuples, according to this, if you have two tuples with the same AB, they must have the same C. According to the second one, if they have the same C, they must have the same D and E. So you can say that it should hold that if they have the same AB, then they have the same DE. So generally, when we reason about functional dependencies, we are going to use X implies Y, but X and Y are sets of attributes, like A, B, C, and D, E, F, right? So assume that these are sets of attributes. So I'm not going to just write A, B, C, or, yes? That is also true. Okay. So they're actually, so the same way with relational algebra, which I'm sure you all love by now, you have multiple rules, and some of them are necessary, the others are kind of derived. So these are the basic rules. So, for example, if y is a subset of x, then x implies y. Okay? So this is the most simple rule. This is actually what's called the trivial rule. So for example, something like A and B together implies A. If you have two tuples that have the same A and B values, then they will have the same A values, right? And this is true for any relation. I don't really have to think what my relation is. This is always true, so it's trivial. This is actually a useless piece of information, so you should really not be saying this. It's the first thing, we don't want trivial functional dependencies, right? So there's actually, this is not called trivial rule. This is a trivial functional dependency, but this is actually called reflexivity. The second one we just did. If x implies y and y implies c, then we have x implies c, which is called transitivity. Okay? So then we have slightly more interesting ones. So if I have if x implies y, then xa implies ya. So you can put the same thing on two sides, right? So if given the same values of x, you have to have the same values of y, then given the same values of x and a, you're going to have the same values of y and a. A is given, and the other one is implied by the functional dependency. Okay? Now, this does not mean that if you have A, B, and C implies A, D, that you should just get rid of these two. No, no, no. That is not true. Okay? You cannot do that. We will see the rule in a second. Okay? It just says that if you have ABC implies, for example, D, I can add the same attribute, ABCE implies DE, or ABC implies CD, I just put C. And I'm treating these as sets, so I don't repeat the same value, but I don't write it as set just to make it simpler to write. So this is called augmentation. These are actually the three crucial ones, I believe. But you actually use the other two that I'm going to give you more frequently. So you can say if x implies y1, y2, then x implies y1 and x implies y2. This is called the splitting rule, that stuff on the right-hand side you can split. So if I had, this was exactly the question somebody asked, if I had A implies B and C, I can also say A implies B and A implies C. That's pretty simple to write. Okay? And the reverse is also true. So if you have X implies Y and X implies Z, then you can write X implies YZ, which is the combining rule. Okay? So you can take this and split into these two, or you can take these two and then compose into the other one. So the most important thing is that the right-hand side is an OR, right? So you can do whatever you want with the right-hand side, but the left-hand side is an AND. So read this as, for example, if I have this, right? This tells me that A and B together implies D or E, right? So if you have the same A and B values, then you will have the same B value, and you will have the same E value. You can say that in one rule or multiple rules. But the left-hand side is indivisible, right? So that's the more important part. So that's why you cannot remove things from the left-hand side in a cavalier way. You have to figure out why you must do that. Okay? So the idea is that if you have some set of functional dependencies, you can derive other ones. So this is the example that I had. It turned out to be a nice example, so let's try this one. So whenever we reason about relations, we don't look at a single functional dependency, but we look at multiple ones, like we were just defining, everything that is true. So generally you are given a relation R, let's say A, B, C, D, E, and F, and a set of dependency rules that are given in a set, such as A implies BC, CD implies F, DE implies D. So one of the questions that I want to ask so if I'm given these sets of functional dependencies, is it the case that AE implies CDF according to this? Because given a set of functional dependencies, I want to derive new ones. Okay? And one way to show that this is actually true in F, because it's implied by F, is use all the rules that we have, and then try to get this using all the rules and the functional dependencies we are given, right? So this actually took me a long time to do on the course notes, so I don't know if I can do it quickly. But so the general idea is that F implies some functional dependency if I can get X implies Y using all dependencies in F and inference rules. Okay? use all the inference rules to see if you can come up with X implies Y. So if I want to do AE implies CDF, okay, we can try. Let's see. So for example, I have A implies BC, so I can take A implies BC, which is given. Then I can augment the two sides by E. So AE, BCE, okay. So I got the right-hand side, the left-hand side, so this is fine. So that means AE implies BCE, that means AE implies BNE, right? Because of the decomposition. So I can decompose, I can throw away something, so I can say AE implies BE by decomposition. Now I have AE implies BE, BE implies D, so I can get AE implies D by transitivity. So given these two, I can use my combining to get AE implies B, D, and E. So this is the combining rule. Now what I want is to get C. That is more challenging. How do I get C? Well, I had AE implies BCE, right? So in fact, that means AE implies C by also decomposition. And this I combine with these two to get actually BCDE. Okay? So I have C and D. Now I need to get F, right? So I can again do AE implies C and D by decomposition. Then I have CD implies F, so AE implies F by transitivity. Then I can combine these two to get AE implies CD and F. I've already moved away. Oh, it's almost there, combining. Right? I'm not saying that this is necessarily the shortest way to do this, but you kind of get the idea, right? So if you're given a set of functional dependencies, then you can get new ones by just applying these rules in the correct way. So this is one way to find if a functional dependency is implied by the rest. So that means that, given these, I can get this one. So it's not new information because I can derive it from that, but it is true, right? If you have the same A and E values, you're also guaranteed to have the same C and D values. Or you can do something slightly different and simpler. You can do a closure of a specific set of attributes. Instead of doing that, so given a relation R and a set F of functional dependencies, X prime, so we say that X implies Y is implied by F if Y is a subset of the closure of X. I have not told you how to do closure of X, but this is the same idea. So the idea is that instead of using all the rules, I'm going to do something much simpler. So I'm going to take a set of functional dependencies and a single set of attributes, and I'm going to look all the things that can be derived using just those set of attributes. So X plus, which is the closure of X, is the set of all attributes that can be obtained from X according to F. Okay. So let's look at the same exact thing that we just had. So what we had was A implies BC, CD implies F, and DE implies D. And I want to know what is the closure of A and E. Okay. So the idea is that if you had two tuples with the same A and E values, what are all the attributes that are guaranteed to have the same value? So if you have two attributes with the same A and E, what are the attributes that are guaranteed to have the same value for A and E? So to start with, if I have the same value for A and E, then I will have the same value for, well, A and E. First, start with what you know, right? So the closure always has itself, right? So you can start with what you know. If you know A and E, then you know A and E. So this is kind of how I initialize, right? So initialize that x plus should be equal to x. All right, now I'm going to use the rules. I'm going to look at any rule that has a subset of these. So do I have a rule that has AE or A or E? I have A. So if I know A, if A is unique, then what are the values that are supposed to be the same? B and C. Given A, I can find B and C. So given A, if two attributes have the same A value, then they must have the same B and C. So I am going to add B and C to my list. Okay. So find any functional dependency, the left-hand side is a subset, then add the right-hand side. So can I apply C and D now? Can I apply C and D? Because I don't have D in my set, right? If I know C and D together, I can get F. But if I know B and E, I can get B and E, I can get D. Do I have B and E? Yes, I have B and E. That means I can add D. So I am going to add E. Okay. Now I have C and D. Then I can actually add F. So I can say so given A and E, these are all the attributes I can find. That means, for example, AE implies CDF is actually true because C, D, and F are actually in the closure, right? So this is implied by F because of the rule. Because C, D, and F is a subset of A and E closure. Is it the case that AE implies A, B, C, D, E, and F? Is it the case? Yes, right? Since the right-hand side is a subset or equal to the closure, then this is also implied by F. Okay. So what would that mean? That would mean that given A and E together implies all the attributes in the relation, that A and E should be a key. Okay? Actually, technically, all I can say right now that it's a super key. But unlike superheroes, super keys have no special powers. So super keys are actually lamer than keys. Okay? So that just means that AE is a superkey, okay? And it may be a key too. Right? But we don't know for sure. Right? So let me give you the rules for these two, and then we'll come back to this. So, there's a lot of definition in this part of the class. Just bear with me. Okay? Superkey just means the superset of key. So if you have a relation R and a set F of functional dependencies, you see now every part in this part of the class, we are always looking at the relation and all the functional dependencies that are true for it, right? And I don't really care right now if those are like a super minimal functional set of functional dependencies. Throw in everything that you know that is true, take that set, okay? We don't care if that is really a smallest set until we come to use that set to decompose, okay? So right now, all we care is that F is everything that is true for R, okay? We say that X is a superkey if X implies Y is true with respect to F, and Y is all the attributes in R. Okay. This is exactly the rule I was telling you before, right? If the given set of attributes imply everything else, then it's guaranteed that no two tuples can have this different values for attributes in X. Okay? So this basically tells me that attributes in X have to be unique in the relation. Okay? So this is kind of basically the main rule of a key. But what is also important is that for something to be a key, I have one more rule, okay? So the same thing is true. X is a key if, one, X is a superkey, and two, no subset of X is a superkey. Okay? There are lots of things that could be unique, but I don't really care about all of them. I'm interested in the smallest possible thing that is a key. So that my keys have to be unique and minimal. All right? So for example, if I go to this example that you've already objected to, okay? So in here is ID a key, okay? Is ID and name a key? ID and name is unique, right? But ID and name is not a key because ID itself is a key, right? So this is a key, but this is only a superkey. So we are always interested in the smallest possible thing that is a key. So going back to this example here, okay. Now I do know that AE is a superkey. I need to show that A or E are not keys, right? So I need to find the closure of A and the closure of E. Okay? And then see if they are actually keys. If they are keys, then AE is not a key. Okay? So what is the closure of A? Start with always putting in the attribute that you know. So I'm given A, I put A. Given A, I can find B and C. Anything else? No. Okay? So A is not a key. How about E? Given E, I can find E. And anything else? No. So this is good. These fail. So AE is in fact a key. Okay. Can there be more than one key? Sure. So we are going to give like a 5-minute break. But when we come back, we are going to work on keys for the following. No. These relations, we are going to find the keys. Okay, so let's give a break here and then we'll continue from here.